Hello and welcome. In this video, I'm going to show you how to differentiate by first principles. Differentiating by first principles is not very easy and is one of the things that causes students the most trouble. So in this video, I'm going to try to slow it down and make it as simple and easy to understand as possible. This will be a little bit of a longer video, but if you can understand this, it will make your future studies of calculus a lot easier. So let's start off nice and simple. What actually is the derivative? Well, if you have a graph, say we have this graph here, it can be any graph, let's just use this one here. The derivative gives you the slope of the line at a particular point. That is very hard to do when you don't have a linear equation, because you can't just use 2 points. Graphs that are not linear are changing all the time. So this point here is different from this point here, which is different from this point here. Even points that are right next to each other are different. The derivative allows us to find the slope of that particular point. This line here is called the tangent. The tangent is the line that crosses and only touches the curve at one point. It doesn't touch it 2 times, so not once here, once here. It goes directly and only touches your curve at one point. The derivative allows you to find the slope of this tangent. So it allows you to find the gradient or the steepness or the slope of this line at that one particular point. So that's why we use the derivative, and in this video we're going to look at how to find the derivative using first principles. Okay, now that we know what the derivative is, let's look at how to derive by first principles. This is where things get a little bit more tricky. So let's draw a basic graph here, and let's say we have this curve here. And on this curve, we're trying to find the slope of this point right here. This one particular point. Now, if we were usually doing this with a linear equation or a straight line like this, we would draw a second point, say over here, and we would use these 2 points to calculate rise over run and give us our gradient. The problem is our curve is always changing because it's not linear, so we cannot do that. So we're trying to find the steepness of this point right here, which is a line that would end up being about here. So let's call this point x, and we'll call this f of x, which is just the y value that the function will give us. And if we come over to this point here, we can call the x coordinate of this point x plus h, and that means that this distance here is h, so we're just taking our x value and adding h, which gives us this point here. So it's x plus h to give us this distance here. And that means that the y coordinate of this point will be f of not x, but f of x plus h. So we have our 2 points here. We have x comma f of x, and then up here we have x plus h comma f of x plus h. But if you remember, we are trying to find the slope of this line here, which is at this one point. We are using 2 points right now. We want to get it just to the one point. To do this, we're going to use something called a limit, which is abbreviated to just LIM. Now, here's where we get our equation for deriving by first principles. So, to find the derivative, we use the same equation as we use when we're trying to find the gradient of a straight line. However, there's a twist. If you remember, the equation to find the gradient of a line is y2 minus y1 over x2 minus x1. So that means in our case, the equation would be our y2, so y, and our y2, so f of x plus h. So we have f of x plus h minus y1, which for us is f of x, over x2, which is x plus h, minus x1, which is x. So now we have our equation to derive by first principles. And if we do some brief canceling out, we can simplify this to f of x plus h minus f of x over, down the bottom we just have h because this second line here, we do not need these brackets, so it's the same as x plus h minus x, where the x's can cancel out, leaving us just with h. But like I said earlier, there's a twist to this. It's not the same as a straight line. There's really just the one point. That's where we use something called a limit, which you may have covered earlier. The limit brings this dot here, or this point here, closer and closer. So our line gets more and more and more accurate. And we want to get it so accurate until that point's almost on top of this point. So the 2 points are so close to each other that they're nearly identical. That way we can find the equation at just the 1 point. Once we have that, we'll have a tangent that crosses through and touches our point at just the 1 stage. We want to get it as close to that as possible. Therefore, we write limit, which we abbreviate to LIM, h arrow 0, which we say as h approaches 0. So in other words, as h, remember h is the additional distance after x. As that gets closer to 0, if it's 0, it's just x. So in other words, we're finding this equation as h gets as close as possible to x. So close that we have a tangent where this line only crosses and touches this point at the 1 point. So if we add that to this equation here, we will get our full deriving by first principles equation. And that equation is f of x, which just stands for the derivative, as h approaches 0. And then we put our equation that we found here. So f of x plus h minus f of x all over h. And that's our equation. And now we have finally arrived at our definition of our derivative. This is how we derive by first principles, using this equation. Okay, so now we have our definition. I've moved it up here to give us some more space. The whole first half of the video has been about how to get this definition. Understanding how this definition is gotten will help you a lot out later in calculus, because as you go through these problems, you understand why this works the way it does. You're not just going through blindly following formulas. So it's very good to understand how this comes from rise over run, where all the values are from, and how the limit works with h approaching 0. But now that we finally have this definition, we can actually solve our problem by first principles. So let's say our problem was find the derivative of 3x squared. So to do this, all we have to do is use this definition here. That means that the first line of our working out will be f dash of x is equal to f dash of x, remember, is just the derivative. So our derivative is equal to, we're going to include our limit as h approaches 0. Now this will be a few lines of working out, and on every single line of working out, you're going to want to include this. Whoever marks your tests or your examiner, if they're even the slightest of a harsh marker, they will take marks off if you do not include this in every line of working out. It's a mistake that lots of kids make, but it's something that's so simple and easy to do. So make sure you're always including it in your lines of working, every single line, and that will help you avoid losing those really silly marks. Next, we're gonna put this into our definition up here. So we're gonna put our 3x squared into our f of x plus h and our f of x. So if we do f of x plus h first, our x is going into all of x plus h. So our x becomes our x plus h. That means that we get 3, so the 3 stays out the front here. But then we have our bracket and we have our x plus h. and we have our squared on the end. The tricky part here that most students make is the squared doesn't go by the x because this is now x plus h. So the squared will go at the very end. Then we have minus. Don't forget to pick up this is a minus sign, not a plus. F of x. So x becomes x. So we have 3 and then our x and our squared. And that's all over our h. So now we have put our function into our definition and we just need to work down until we find our derivative. Remember, you always have to include your limit as h approaches 0 in your workings. However, you don't have to include the f dash of x. Just include the equals as h approaches 0 and then all your workings. And we can start solving this. If we expand these brackets here, the difference of two squares, we get x squared plus 2xh plus h squared, and that's minus 3x squared. And it's all over h. And if we keep working down, we have our as h approaches 0, and now we can expand these brackets. So 3 times x squared gives us 3x squared plus 6xh plus 3h squared, and then at the end we have our minus 3x squared. And that's all over h. We continue working down with as h approaches 0, and this time we can do some simplifying. If we look up here, we have 3x squared, and then at the back we have negative 3x squared. So those can cancel out. That leaves us with just 6xh plus 3h squared all over h. And as we continue working down with as h approaches 0, we can see that h can cancel out here. We can cancel this h with the 2 up the top, so here, but be careful because this is h squared, so just the squared leaves. That gives us 6x plus 3h. Now we'll write this up here just to give us a little bit more space. But if you remember, there was a twist. This is not the same as rise over run. We have our limit here as h approaches 0. Because remember, we want to get h as close as possible to 0 so that we just get our tangent and our derivative or our slope is as accurate as possible. Therefore, we're actually gonna substitute 0 in for h. And when we do this, we can finally drop our as h approaches 0 because we've actually subbed it in. So for this last line of working, you just have your 6x plus 3 and we substitute our 0 in for h. And that will give us 6x and 3 times 0 is 0, so our final answer, our derivative, is 6x. And that's how you find the derivative using first principles.